Hello friends, I am Nihal Rajpal. In this video, we have seen the implementation of registers as well as our carry flag, and this video is a part of our implementation series. So if you have not seen the previous video, then I suggest you to please follow the sequence. So let's start with registers. So we have created a separate component for the register itself. So many of you will ask why we have created a separate circuit for the register itself. Now the reason is the registers which are provided by Logisim were very basic. They don't even contain the common signals like increment. And because the functionality of increment is so common that it is required in many of the instructions. In fact, some registers like PC needs to be incremented after every instruction. So we just thought that it would be a great idea to create a separate circuit of register with increment signals introduced in them. So let me show you the register circuit. So this is our address register and it is a 12-bit register because our address is of 12 bits. So from the main circuit, we are taking the data input as an input for this AR circuit for this address register. It is given to a bit extender. So a bit extender will truncate the four most significant bit and will give us the 12-bit input. So the four most significant bits are actually discarded. Now this is required because the common bus with which this address register is connected in the main circuit is of 16-bit. So this 16-bit line needs to be converted to a 12-bit line before it is given as the actual input to our address register. And second input to this multiplexer is the incremented value. So the output of this register is given as the input to this adder, and the other input to this adder is a value 1. So whatever the value that will be stored in this register will be added with this one, hence it will be incremented and given as the input to the line number 1 of this multiplexer. So whenever this increment signal is 1, the incremented value will be given as the actual value for our 12-bit register. And when this increment bit is 0, our actual value which is coming from the common bus will be considered as the actual value for this register. And this increment signal is also given as the input to this OR gate, and second input to this OR gate is our load signal. So we have to load our register whenever either our increment signal is 1 or either our load signal is 1. So when our increment signal is 1, the register will be enabled, and during the next clock pulse, the register will be incremented. So currently 1 is the value. So this incremented value will be 2. And because INR is also 1, 2 will be given as the value. So during the next clock pulse, 2 will be accepted by the register. And when this INR is 0, the value which is coming from this data input will be accepted by the register. So for this, we need to enable the load signal. So and during the next clock pulse, this 0 will be accepted by our register. For the output, we are giving two outputs to our main circuit. One output is a 12-bit output and another one is our 16-bit output. So this 12-bit output is actually given directly to our memory, while the 16-bit output is given to the common bus. So let me show you in the main circuit. So here on the top we have our data output which is of 12-bit and it is given to our memory, and the 16-bit output is given to the common bus. Same is the case with program counter. It contains the same circuit, but here we are only taking a 16-bit output because there is no requirement for a 12-bit output. Now you might be thinking what this component is doing here. So this component is a pull register. So this pull register is used to handle the case when this INR signal is left unconnected from the main circuit. So suppose this INR signal is left unconnected from the main circuit, then this line will go in the floating state, and which will actually create the problem while selecting. So this pull register will say that whenever this line is in floating state, then the value from this pull register must be considered as the actual value. But as of now, this line is not left unconnected. So whatever value will be given to the INR will be considered as the actual value. So suppose this line is unconnected, then this value will be considered. So that is the simple use of this pull register. Now let's see the other registers. So PC has the same implementation. DR also has the same implementation with just one exception that uses a 16-bit register. Then we have AC, which is accumulator. So accumulator has one more thing, which is the external input. So our basic computer also contains an instruction, which is IN. So IN accepts the value from the external input and gives it to the accumulator. So this is used to handle that situation for IN instruction. So our input register is this one. Value of this input register is directly given to the accumulator, and whenever this input loads signal is enabled, then the value from this external input must be considered. Otherwise, whatever value is given from the actual input should be accepted. And the external input is of 8 bits, so it needs to be converted to 16-bit before it is directly passed to the register. And for the output, it is giving the 16-bit data output to the main circuit, which is in turn connected to our common bus via a multiplexer. In the similar way, other registers like IR and TR are also implemented. So next, let's see about our carry flag, which is the interesting one. So this is the circuit for our carry flag. So from the external circuit, we are taking the value of the carry flag as the input. Along with that, we are also taking one more signal, which is the CMP. So CMP stands for the complement. So we have made the circuit for carry flag just for one instruction, which is CME. So CME stands for complement E. So when the CME instruction is encountered, we have to complement the value of the carry flag. So if carry flag is 0, then we have to make it 1. If it is already 1, then we have to make it 0. So this complement signal is given as the select input to this multiplexer, and line 0 of this multiplexer is connected to the actual value of the carry flag, which is coming from the external circuit, while the line number 1 of this multiplexer is connected with the Q dash, and Q dash is nothing but the complemented value of the carry. So currently the value of the carry flag is 0, so Q dash is 1, and this Q dash is given as the input to this multiplexer. So whenever the CMA instruction is encountered, we will make the CMP signal 1, we will make the load signal 1. So what will happen is, during the next clock pulse, the value of the carry flag will be complemented. If it is 1, then it will become 0. If it is 0, then it will become 1. And when this complement signal is 0, then the actual value of the carry, which is coming from the external circuit, will be considered. So that was all for this video. In the next video, we will start with our arithmetic and logic unit. Thank you.